Now let's show the example that we mentioned earlier, the rivet and bridge example. Let's say that we have a bridge and we know the true value is 10,000 centimeters, as you can see here. But when we measured it, we measured as 9,999. So this is the length of the bridge. $10,000. The actual value. Similarly, we have a rivet application, and a rivet means a connector. Actually, it connects two or more parts. You can see two parts here, and it connects them by attaching them to each other. And we know that the length of this is a small component actually, and this is just 10 centimeter, the true value. But when we measured it, we measured 9 centimeters according to this example. So we want to calculate the error for each case. Simply the true error and the true percentage relative error. So let's calculate them, especially first the true error. For the let's start with the rivet, and we say ET rivet. True error is shown by capital ET, and ET rivet is, we know that this is true value minus approximation. So true value is 10. 10 minus the approximation is 9. Then 1 centimeter. Similarly, we can use the same formula for the bridge, ET bridge. At this time, we will use 10,000 as the true value, as stated here, minus 99.99 as the measured value or predicted value. And we see that again we have a 1 centimeter error. You can see that both of them have the same error value, 1 centimeter. But when we look at the magnitudes, actually rivet is in magnitude of 10 and the bridge is in magnitudes of 10,000s. So having a 1 centimeter error in a magnitude of 10 and magnitude of 10,000 is actually relatively so different. Here we actually made a very good measurement. Or if we manufactured this with this value and expected what was this one, we made a good job actually here. But over here, between 10 and 9, this is a very large difference actually. Even though 1 centimeter is the same, the difference is relatively large. And because the magnitudes are different, using true error as the error metric may lead us to the wrong way to interpret these. So we can say both have 1 centimeter error, but magnitudes are different. Magnitudes are different. That's why we want to use the relative percentage error or percent relative error. Let's say B, percent relative error. Remember that this was shown by Ch03 and it was equivalent to true value minus approximation divided by true value times 100%. Simply we normalize by x. And for rivet, let's say Ch03 rivet 10 minus 9 divided by 10 times 100 is equivalent to 10%. And for the bridge, ET bridge, this is 10,000 minus 99.99 divided by 10,000 times 100, and this is equivalent to 0.01%. So you can see here that this is a very big error actually. 10% is large, especially compared to this one. This is only just 0.01%. We see that this is a large error or big error in measurement. We didn't make a good measurement work actually. We can conclude that, but in here we made a good job. Let's say low error means good job on measurement, on measuring the bridge. So this is important to have this interpretation. That's why we prefer to use percentage relative error. As you can see, this is a very nice example to simply show how effective it is.